right, so just coming back to the hair cell structure. Uh, so as we said in the previous video, we said we have three outer hair cells and one inner hair cell. So they would go in this way um, along the cochlea, and then inside you have one line of the inner cell. But actually, what you see is that their hairs are embedded into the tectorial membrane. And this embedment is such that when there is a vibration that goes on, this tectorial membrane also moves. So if it moves, because remember this fluid here, and the fluid that is here is high in potassium, low in sodium, known as the endolymph, whilst in the scalar tympani we have perilymph. Okay, so the vibration that is being caused is going to send a shaking, and this shaking is going to cause the tectorial membrane to move. Once they move, you find that these hairs that are embedded in the tectorium cause those hairs to also move. Um, so the movement of these hairs is such that what we have is, I'll say this is the afferent, okay? And then we have the cell, the hair cell here. And the hair cell, the hairs themselves are such that we have the usually non-motile large one known as the kinocilium, and then we have shorter hairs that come through, and these are motile, they move. Um, so you see that if the tectorium moves this way, because of the tip links that link these hairs together, you see that even these ones will move that way. But once they move, they will cause a stretch, a straining, and this stretch is going to open up these potassium channels. And these mechanically gated potassium channels will then allow an influx of potassium. So when potassium goes into the cell, you find that there's increase um, in there will be depolarization to take place, and depolarization is then going to cause voltage-gated calcium channels to open up. Once they open up, there will be an influx of calcium, which will allow for exocytosis of the neurotransmitter. And once the neurotransmitter goes out, you find that there's now initiation of an AP, an action potential in the afferent. And in this case, we're talking about cranial nerve number 8, which will then take the action potential to the central nervous system. So this is what we're talking about. This is their basic structure. This is how it's going to move from mechanical to electrical. Okay? Uh, but what we see here is the outer cells are innervated as well by efferents. Okay, so these are afferents and these are efferents. So efferents go too. Um, why do we have an efferent innovation here? So the innovation here is so as to hyperpolarize. So you find that these release SEH onto these cells, and they cause them to hyperpolarize. If they hyperpolarize, it means there is a reduction in the amount of neurotransmitter that is then released from the outer cells. So what's the physiology there? Why have these cells actually go through hyperpolarization? Why do we want that to happen? So this is initiated by the olivocochlear component. So the olivocochlear component is going to be um, stimulated by various situations, such as an increase in sound, loud sound. If there's loud sound, you find that the olivocochlear area is stimulated, and it is then, or is activated, and then going to release SEH onto the outer hair cells. And once that happens, you find that hyperpolarization actually happens. When there's hyperpolarization, there's a reduction in the neurotransmitter that is being released, and therefore you won't find action potentials moving as much in the afferents. That's not to say, remember, that is not to say that there are no afferents that are coming in from the outer cells. Though the primary sensory cells are the inner cells, we see that the outer cells respond more to sort of this feedback mechanism, so that there's a reduction in the sound that is then going to the central nervous system. So now that we have sort of learned about what is happening, let us start from what happens from A to Z. So first of all, just gentle reminder on the mechanism of sound transduction. So sound is a wave, really. It's a pressure wave, and it is characterized by amplitude. All right. So amplitude is simply how loud a sound is. So this is volume. It's based on volume, and it is measured in decibels. And then it is also characterized by frequency. So frequency, measured in hertz, is about pitch. Okay, it's about pitch. So this is just how high the sound is, or how low the sound is. So you find that several characterizations can be measured using a graph. So if the amplitude is high compared to a lower amplitude, you find that the sound is louder here and softer. The volume is low. And when it comes to frequency, when you have slow frequency and then increased frequency, there's a difference. Okay, so here what you hear is a low pitch, and what you hear here is a higher pitch. I hope that was you can tell that. So it is low or high. It is soft or loud. All right. So the latter is amplitude, and the former was frequency. So amplitude causes maximum vibrations to happen if it is high. Okay, it causes maximum pressure changes in the eardrum. So the eardrum will be vibrating a lot, and then you have a louder sound. But when the vibrations reduce, then you have lower volume. The maximum safe exposure has been noted to be 85 decibels. Usually higher than that, you get headaches or hearing damage. For example, rock concerts are usually at 120 decibels. An iPod could go all the way to 100. Try to check Ganong or Perv on a list of these. In terms of pitch, you find that human ranges from 20 to 20,000 hertz, and the average for female is 20 hertz. Um, Rather, 20 hertz is actually for males. For females, about 250 is higher. All right, the high frequency. Uh, what's the physiology here? We said it's about the eardrum having more vibrations. When we talk about high frequency, we are now talking about the cochlea. All right. So remember, we said that there's the helicotrema there on the apex, and then this is the base part of the cochlea. So when you have high frequencies, okay, high frequencies, which are these ones here. When you have high frequencies, you find that it will stimulate the base of the basilar membrane. Okay, so this is the base. So it will stimulate this part of the basilar membrane. While if you have a lower one, it's going to stimulate the apex. Okay. Um, so this is like a reverse keyboard, if I may say, because this is high and then that is low. So again, high frequencies stimulate the base of the basilar membrane, while the lower ones stimulate the apex. And remember that low ones is low pitch, and high ones is high pitch. You can distinguish pitch. It's trainable. You're able to distinguish pitch better rather with training, and yeah, sound quality. Just using these two can be studied, but that is studied in other courses. So from here, then we talk about sound transmission. So really, this is just a reminder of the physics that you learned on sound. So acoustic energy in form of sound waves is channeled to the ear canal. We remember that. So the sound waves, first of all, strike the tympanic membrane, causing vibrations, okay, drum-like, and then we have mechanical energy. So it moves from sound energy to mechanical energy. So let's just have a clean thing. So yeah, so you have sound, and so this is acoustic. So the acoustic energy through the eardrum is changed to mechanical energy. The mechanical energy, okay, then through now the bones, okay, is transferred into the inner ear, okay, it's transferred into the inner ear through the oval window, creating vibrations. These vibrations are still mechanical energy. So this mechanical energy, depending on the frequency and the part of the, depending on the frequency, you find that a particular part of the basilar membrane will vibrate, and the vibrations, of course, will depend on how on the amplitude. Okay, so once that happens, you will find that it will result in the movement of the organ of Corti. So the organ of Corti will have this shear movement, and then the tectorial membrane moves. So once the tectorial membrane moves, okay, so what we have there is this. So you have the vibrations coming in, and then this will move depending on which part. Let's say it's a low sound. So you find that immediately after the helicotremor, you have this vibration that happens. Okay, so once this moves, it means that the organs of Corti that are centered around this area are going to vibrate. Okay, so when they vibrate or when they move, then they will initiate this um, electrical energy. So the electrical energy I beg your pardon. The electrical energy will then be transferred through the auditory nerve to the brain, where there is now interpretation of what you have heard. In the next video, we'll be looking at the auditory pathway. Okay.